Alright, in this video we're going to talk quite a bit about Newton's method. And so maybe the first part of this video is going to just be reminders from Calculus 1 about how Newton's method works. And then maybe by the end of this video you'll learn something new that will apply to our project this semester. To begin, we'll remind you that the definition of the derivative is this. I can write f prime of x to refer to the derivative of the function f with respect to x. And that would be defined with this limit, which I'm sure you've seen 100 times before. If you are asked then for a tangent line approximation, here's what that means. It means instead of taking the limit as h approaches 0, we're going to allow h to be some small positive number. And heck, it doesn't even have to be a positive number, it could be a negative number. But as long as it's relatively small in absolute value, that's going to be fine. Then, this derivative is going to be only approximately equal to f of x plus h minus f of x over h. Right? Equality only happens in the limit, but if we're just allowing h to be some small number, then this is now an approximation. So the squiggly equals means it's approximately. Okay? Now let me rearrange this a little bit by multiplying both sides by h and then, adding f of x to both sides. And if I make those rearrangements, I'm going to get the equation f of x plus h is equal to, or approximated by, I guess I should say, f of x plus h times f prime of x. Okay? And this is what we mean whenever we talk about the tangent line approximation. This right here is the formula for a line, right? You've seen the slope-intercept formula for a line, y equals mx plus b. What I'm trying to approximate is the value of my function at the point x plus h, and my slope is going to be this derivative. That's the slope of the tangent line. H is going to be my sort of x value, my variable here. And then, of course, b is going to be this f of x value, right? That's the height of my function above the x-axis, or the value of my function whenever h is equal to 0. But anyways, this is the formula for a tangent line. And this tangent line approximation is pretty darn good. In fact, another way I could write this is I could write f of x plus h is equal to f of x plus f prime of x times h plus, and then what I'm adding on the end here is an error term. So I can write the equal sign and not just the approximation, because I'm saying, this value of the function here at x plus h is equal to all of this, but with some error, and so the error is just sort of described by this term. This term tells you how much error there is in this approximating formula. But what makes this a good approximation is that, of course, if I take the limit as h approaches 0 of this error term, it's 0, right? In other words, I'm saying if h is 0, then there's no error at all in this approximation. So if h is 0, this term goes away, and this x plus h just becomes x plus 0, and what I'm left with is f of x equals f of x, and of course there can't be any error term to add on to this because that's already true. That's kind of a given, and you don't need the tangent line for that, right? You could use a different slope, a slope other than the derivative, and you would still have this as being true. What makes this a good approximation is that if I take the limit as h approaches 0 of even this, the error term divided by h, this still equals 0 as h approaches 0. And that's saying something important, actually, because this denominator, this h is going to 0, and typically when the denominator gets really, really small, then the value of the fraction gets really, really large. But in fact, this error term is approaching 0 even more rapidly than h itself is approaching 0. And so this is sort of a statement that tells you that this is actually sort of a valid approximation and that this actually means something. In case you've never heard this before, I want to actually demonstrate what this kind of looks like using Desmos.com, and so let me pull up Desmos.com real quick. And so, for the sake of argument, let's come up with my function f of x and let it just be the sine function. And what I also want to plot on here, I'll go ahead and make it look nice and pretty too. What I want to plot here is also the tangent line approximation at some point h, wherever I want that to be. And so let me set, the reason I have to change the names of my symbols so much is I'm trying to get Desmos to work the way I want it to. So here we are with my function and the tangent line approximation of that function, right? The tangent line approximation is in purple, and it's tangent to my function where this black line intersects the function, right? So at that particular x value. Now, let's calculate what that error term is. And of course, my error term, I'll give it the name P for error. No, maybe capital E. We'll say capital E is just going to be my function minus this g of x business, right? And so now my error term is in red here. And you can see that wherever I have this tangent line approximation actually meet the exact value of my function, then the error should be 0. And so that's why where this black line intersects the x-axis, that's also where this red error curve intersects the x-axis, right? So the red line, or the red curve, is telling me the difference between my blue function and my purple approximation at that point. But what I also promised is not only that the limit, as we get to this point on the red curve, is 0, but I said, what if I even take the error term and I divide it by x minus a. And even in that case, where I divide this error term by x minus a, even in that case, now what is now a blue curve, and maybe I should make it orange, even now that orange curve is always going to be 0 wherever that black line intersects the x-axis. So I understand there's a whole lot going on here. But again, what makes this a good approximation and better than any other linear approximation is that even this orange curve is 0 at this point, right? That sort of was what tells me is that it's a tangent line. Now, let me try a different approximation where I replace this derivative in my slope with some other slope, right? So instead of having a slope of, I don't know, something that's Let me move it over here. So now that's kind of close to like +1. What if I replace this with a slope of like 2? So now this is no longer a tangent line here in purple. Like I promised you, other approximations can give you a 0 for the error term as long as they intersect the actual function right there. But now this is not a good approximation because this orange curve, which represents, the error term divided by that h variable, now that doesn't have a limit of 0 at that point. Anyways, hopefully that sort of makes sense, and that's kind of a neat visualization if you've never seen it before. And how we're going to derive Newton's method is by beginning with this tangent line approximation, which says f of x plus h is equal to f of x plus f prime of x times h. And of course I could add the error term on the end, or I could just say that this is an approximation. Meaning not exactly, but approximately. Now, the goal of Newton's method is to find zeros of a function. So if we happen to be given x and my function, what we want to find is an h value, or more specifically a value x plus h, such that f of x plus h is equal to 0, right? That would sort of tell me where the zeros of my function are. I just know that 0 exists at x plus h. And so ideally, this is what I'm trying to look for. I'm trying to look for f of x plus h equals 0. So let me just go ahead and do that. I'll just replace that with a 0. And 0 is approximately, f of x plus f prime of x times h. And if I'm already given x, then what I'm really looking for is h, right? And so I can rearrange this a little bit, maybe subtract, f of x from both sides, divide both sides by f prime of x, and that's approximately what h should be. So if I start by given some x value, and I plug it into f of x, and f of x is not equal to 0, the next thing I should try is choosing the value x plus h, and then plugging in f of x plus h. And again, that's not going to be exactly 0, but it should be closer to 0, right? Ideally, this approximation working, if I'm in a close enough neighborhood to the 0, then this might actually get me closer to 0. It'd be approximately 0 in some sense. This could be made a little bit more clear with the second formulation that I gave for this tangent line approximation. And let me sort of show you what that would look like, right? If I replace this with f of x is equal to f of a plus f prime of a times x minus a, let's see how that would sort of change this derivation and make it, pretty much the same, but maybe even a little bit more clear what we're supposed to be doing here. And in this case, rearranging this equation and saying, well, if I'm given some starting point a, I'm given a function, and I want to find a value for x such that f of x is equal to 0, right? I'm trying to find the zeros of this function f. Then I'm just going to set f of x equal to 0. And then that way 0 is approximately the same thing as f of a plus f prime of a times x minus a. And now if I subtract f of a from both sides, that goes on the left. If I divide both sides by f prime of a, then this is now approximately equal to x minus a. Again, the same thing, but I think this makes it a little bit easier to see. Now if I'm trying to solve for x, I just have to add a to both sides of the equation. So that tells me that x is approximately equal to a minus f of a over f prime of a. So remember, a is something that you were given to start with. X is going to be a better guess at what a zero of this function will be. Actual Newton's method, if you were to look it up on like Wikipedia, says this. It says x of n plus 1, or x with subscript n plus 1, means it's the n plus 1th iteration of x, is, I'll actually write equals, because now I'm not talking about an exact location of a zero, I'm just telling you about what method we're going to be using. This is the formula for Newton's method right here. We'll write xn minus f of xn divided by f prime of xn. So the way Newton's method works is you are given x0. Then the first thing you're going to find is what is f of x0. And you're going to find what is f prime at the point x0. And then I would have x0 minus f of x0 divided by f prime of x0. That would be the formula for x1, right? I can use, if n is equal to 0, then this formula becomes x subscript 0 plus 1 is equal to x subscript 0 minus f of x0 divided by f prime of x0, right? So that's how I'm going to find x1, and then after I've found x1, I'm going to find f of x1 and f prime of x1, and using x1, f of x1, and f prime of x1, I can then use the Newton's method formula to find x2. And so all of these different values of x, x1, x0, x1, x2, x3, and so on, these are what we call the iterates. And you can make a sequence with infinitely many iterates, and this sequence, again, if everything's working as we hope it should, if everything seems to be working correctly, then we expect these iterates to be getting closer and closer to the value of x that gives you a 0 for your function. And so what we could say is that the limit as n approaches infinity of f of xn is 0. Of course, this is what we expect to happen, or what we hope to happen, but that's the ideal case, and not every case is perfectly ideal. We can show you some cases where it's really not, it doesn't work out ideally. Anyways, that's how you find Newton's method. Now let's work some examples. Suppose we wanted to find the zeros of this function right here. I'll let you pause the video, and when you pause the video, please just go ahead and work this out by hand using Newton's method, right? So this is your function f. You find the derivative formula for this function, and then take several iterates. Maybe take 3 or 4 or 5 iterates. As an initial iterate, I want you to start out with 1. Obviously, obviously x equals 0 is a 0 of this function. So I don't want to start you with the initial iterate x equals 0. But try x naught equals 1 and then do Newton's method to it. Now I'm going to move on, assuming you've already calculated a sequence of iterates, starting with this initial iterate using Newton's method on this function. And what I'm about to show you is what this would look like on Desmos. So here this red curve is that function we've been talking about. If you started with the initial iterate x equals 1, then this is the value of the function you would calculate, right? Something like negative 1.2375. And this line segment, this diagonal line segment that makes the bottom of this triangle, that is the tangent line approximation of this red function at the point x equals 1. So we follow that tangent line approximation to calculate a 0 of the tangent line approximation, and that becomes the next iterate for finding the 0 of my function. So then I end up with the iterate x equals like 0.2-ish or something. And then take the value of my function there for that x value. This diagonal line here is of course another tangent line approximation of my function at that point. I use that tangent line approximation to calculate a 0 of the tangent line approximation, and then I repeat the process now with the iterate 0.02 to find a value for my function and a tangent line approximation, and then I find a 0 of the tangent line approximation right here at 0.00025 or whatever, and then again calculate the value of my function, calculate a tangent line approximation, and then find the 0 of the tangent line approximation. And that, my friends, gets us very, 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 very close to the 0 of the actual function. And there's another step in the iteration process, but you'll notice that I'm getting very, very, very close using these Newton method iterates to the actual 0. This is a cool little visual I put together on Desmos, though, because I can change the value of the initial iterate, and you can see how Newton's method would evolve if I started from a different iterate, right? So maybe as a challenge, you can start from the initial iterate -2 and see what happens. Well, for the first iteration, we're getting closer. We get the next value of like -1.25. But then, since the function is so flat here, that tangent line approximation fails to give us anything good. Instead, that tangent line approximation flies us way out here, and then it's only after several iterations that Newton's method brings us back in to this 0 over here. So that's an interesting lesson learned then, that Newton's method doesn't always converge to the closest 0, right? If you start with initial iterate -2, Newton's method won't converge to 0, which is the closest 0 of my function. Instead, it converges to this 0 at 3.426. Kind of crazy. Okay? Of course, if I start with something pretty close to 0, then most of the time it converges into 0. And if I start with something pretty close over to 3.4, it'll converge over to that 0 pretty quickly. And that's what it looks like over here. Okay. So that's what it looks like to take the 0 of a single variable function. Let me give you another example to kind of work on and chew on. Let's try this function. Go ahead and try to do a Newton's method sequence of iterates. For this function, if I start you off on the initial iterate, x equals 1/2. So I'm going to allow you to pause the video right quick and try to work up a sequence of iterates. See what you're getting close to, what the 0 of the function might be. And now I'm assuming you've paused the video and already attempted this problem. And to move on, I will show you what this function looks like right here. So now that function is in red, and if I start with the initial iterate 1/2, this is how we visualize that, right? So here's my function in red that I just told you to give your best shot working on. And starting from the initial iterate 1/2, of course, I go up to the value of my function. I create a tangent line approximation. Tangent line approximation, I find a 0, and it generates a new iterate, and I'm getting closer and closer to the actual 0 of the function, which is going to be, you have to zoom in a long way to even find the next Newton's method iterate right there, just because this function is so close to actually being, linear, very, very nearly linear as I go zoom in this close to the origin. So I'm trying to zoom in, I'm trying to scroll in closer and closer, but I don't know how fast to. Oof. Okay, so Desmos kind of breaks down a little bit there, I guess just because round off error and such. But anyways, just only 1 or 2 or 3 Newton's method iterations get you so close to the 0 of this function. Now what happens if I start from a different initial iterate, like I start changing this value of x0? It still works and it still converges up to a point, but then once I pass a certain point, you see how this function is becoming flatter and flatter? So the tangent line approximation is becoming more and more of a horizontal line instead of a steep diagonal line. Well, at a certain point, I'm going to move past and it's just going to start firing off to the extremes, right, to infinity. So in this, what's happening is my initial iterate is x equals 2.4. It's going up to the value of the function. It's creating a tangent line approximation. It finds a 0 of that tangent line approximation. Goes down to the value of my function, creates another tangent line approximation, follows it out here to find the 0, goes up to my function, and then boom, it shoots it off way out there towards like negative infinity, right? It just gets too flat in this part of my function for Newton's method to work. So there are times when Newton's method fails. There's times when it successfully finds the 0 after just a few iterations, and then there's times where it fails to find the 0 of a function. Okay, one more example. Go ahead and take a look at this function. Use the Newton's method formula to generate a sequence of iterates, starting with the initial iterate x0 equals 1. I'll let you pause the video and try that. I'm going to move on now, assuming you've paused the video and you've already tried it, and then we'll take a look at what that looks like if I do this polynomial function. And I start off with the initial iterate where x0 is equal to 1. So here's my function in blue. Starting off with the initial iterate x equals 1, I go up to my function, I create a tangent line approximation, it shoots me down to x equals 0. X equals 0 finds the value of my function at 2, and then shoots a tangent line approximation down and finds x equals 1, and it actually enters the cycle, what we'd call a 2 cycle, of just bouncing back and forth. So hopefully when you tried this and you calculated by hand, the sequence of iterates you would have gotten is 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, and it never converges to anything. And so since that sequence never converges, then I obviously did not find the 0 of this function. Different initial iterates of x will have different results. In this case, an initial iterate of 1.5 comes up with a second iterate of 1, which then enters that 2 cycle. In fact, if I start anywhere kind of close to 1, it should, in theory, do the same thing. Right here I'm not plotting infinitely many iterations. I'm only plotting like 8 iterations, and so you can't always see it. But anything really close to 1 or close to 0 is going to enter that 2 cycle of going 1, 0, 1, 0, 1, 0 eventually. It's what we would call an attracting 2 cycle. If I choose just some crazy values, then of course I can find things that don't immediately converge. They fly off to the right. But then this one, interestingly enough, does eventually find my 0 of my function. It just takes 8 iterations to find it. But anyways, if I start over here, if I start with some value that's close enough to my actual 0, then Newton's method does eventually converge to and find the 0 of my function. Okay, that's enough for finding zeros of functions. Now let's do something a little bit more interesting. Now we're trying to find critical points of this function. This is the same function we did as part of my first example where we were finding zeros, but now trying to find critical points means I'm trying to find places where not the function value is equal to 0, but I want places where the first derivative is equal to 0. Well, the first derivative is itself a function of x, and so what I can do is I can apply Newton's method, right? So I'm going to write down the same Newton's method formula, but with a twist. Instead of writing, well, f of x up here, now my new function is the derivative function. And so I'll write f prime of xn divided by, and now the derivative of this derivative function would be f double prime of xn. And that's what the formula will be for finding critical points of a function. Very, very similar, but this is just Newton's method for finding the zeros of a derivative, and of course the zeros of the derivative function are just the critical points of the original function. And so maybe there's something I can do to my Desmos right here to tweak it, to make it so that it will find the derivatives pretty easily. Ooh, never mind, this is going to be a kind of a intense overhaul, so let me rename it Newton's method for critical points. And that way I don't break it whenever I go in through here. And for each one of these formula, I'm going to now pop in f prime in the numerator, f double prime in the denominator, and that is going to make this visual work to find the critical points of any function that I put in. And there I think we're done. So let's see if it works. Hopefully it works. It kind of works. Kind of, sorta. Yeah, I'd say that's mostly a success. Mostly a success. So try it on your own. Try to use this formula with initial iterate at x not equals 0 and see where we end up. Right? Give that a try. And then to visualize what that would look like, let me set x not equal to 0. And what you should find, ideally, is that it gives you an initial, or an x1 value of negative 0.8, and then it gives you an x2 value of negative 1.05, and then an x3 value of negative 1.269, an x4 value of negative 1.06899, and so on. And then it looks like sort of where this is trying to end up was near this critical point. Or is that a critical point? I guess what we'll have to do is plot the derivative function here. And no, that's not actually a critical point. It's just very close to being a critical point. And so that's why Newton's method seems to be failing, is that's really throwing it off. The fact that this derivative gets so close to 0 there but doesn't actually reach 0. That becomes a problem for Newton's method. Okay? This over here, however, is a minimum. We can clearly see that with our own eyes. And so obviously a critical point of the function. And if I get my initial iterate close enough, then Newton's method does eventually find that critical point. All right, so if you started with an initial iterate of 4, then you should have found the critical point of the function. Okay. We'll do one more example. So here's that function that starts with x cubed. We were looking at that just a moment ago. So there's my function. If I take an initial iterate of 0, that clearly fails. I guess because the second derivative is 0 there, that must be an inflection point of this function. But if I take, almost any other initial iterate, it very quickly finds that minimum. Or if I move over here to the left of that inflection point, then Newton's method also finds that critical point, that maximum of the function, really easily. And so whenever people are trying to optimize functions, that is, you're trying to find the maximum or the minimum of some function, maybe you have a function that you think describes your profit as a good math model of, the profit of your business. Clearly you want to maximize profit, so you want to find the maximums of that function. Newton's method, where we tweak the formula and use this formula for Newton's method to find critical points, that's how you're going to find the optimum values or the maximums or minimum values. Well, really, you're just finding critical points, but you hope that those critical points are the maximum value or the minimum value of your function. That's kind of how it works. It's how a lot of solvers work in real life. But as you've seen, Newton's method is not perfect, and you can't always expect it to be perfect. The next sort of generalization we're going to use for Newton's method here is we're going to extend this to a multivariable function. So now I have the function f, which is a function of 3 input variables, x, y, and z, and this function is also going to be vector valued, which means that it'll spit out 3 different output values. There's 3 different output variables here. So 3 independent variables, 3 dependent variables. How do we find Newton's method to find a 0? Well, a 0 of a vector valued function is the coordinate triple x, y, and z such that the output vector gives 0, 0, 0. Right? That's what I mean when I say we're looking for a 0 of a multivariable function. I want this output variable to have entries that are all zeros. So what values of x, y, and z give an output of this function that gives me 0, 0, 0? What we're going to do is quickly rewrite what the Newton's method formula looks like. So x sub n plus 1 is equal to x sub n minus f prime of x n, oh sorry, that should be f of xn, over f double prime of xn. Oh, sorry, that should be f prime. Gosh, so many little mistakes here. But this is the Newton's method formula for a single variable. Now, the tweak that we make for a multivariable function f is we say x is going to be the name of my vector of independent or input variables. Right, so that was the case for the single variable function where x was just meant a single variable. Now, for the case of a multi-variable function, x is going to be a vector of input variables, not just a single input variable. And we're going to write that this vector xn plus 1 is going to be equal to the vector xn. And we're going to have to start with some initial iterate vector. Minus my function evaluated at some input vector xn divided by the derivative of my function evaluated at some input vector xn. But here's the issue. When we're dealing with a multivariable function, this is a vector. This is a vector. This is a vector. And so how do I divide a vector by by this, I guess what I'm trying to get at is like, what is this? You could divide a vector by a scalar, right? You could divide each entry in the vector by a scalar. But in that case, what would that scalar be? If you take the derivative of a function, you need to be taking the derivative with respect to some variable. It doesn't really make sense to take the derivative with respect to a vector. You could take the directional derivative, but this is just not ideal. Really, what I'm trying to say is a scalar isn't going to be able to contain enough information to really guide our multivariable function Newton's method in the right direction. Instead, this is not a scalar. It's also not a vector because we don't have a solid way of dividing vectors. Right? When we're multiplying vectors, we have the dot product, we have the cross product. But we've never defined a way of dividing vectors. And so what it is it is a matrix. Now, a solid complaint that I would definitely take seriously is you could say, well, we don't have a solid way of dividing a vector by a matrix, right? Like, what would it mean if I have a vector v divided by a matrix M? I know what matrix vector multiplication looks like, right? We talked about that in a previous recording. But what we're going to do instead of dividing this vector by a matrix is instead we're going to multiply the vector by the inverse matrix. Right? So what we normally mean by division is that if I have 5x and then I divide by 5, that this is just x, right? Multiplying by 5 and dividing by 5 are opposite operations. They just cancel each other out, okay? So if I have mv, when I think about dividing by m, it should be an operation that sort of cancels out multiplying by m. Now, this is not well defined, but if I have mv and I want to cancel out the idea of multiplying by m, one thing I could do is multiply the whole thing by an m inverse, because this m inverse times m is just the identity matrix, which is just the vector itself. And so this is the idea. Instead of trying to divide by a matrix, we're going to multiply by the inverse matrix. So we'll first find some matrix that represents the derivative of this multivariable function, and then we're going to take the inverse of it. The best matrix that represents the derivative of this function is called a Jacobian matrix. Now, if I'm calling the output variable f and the input variable x, what the Jacobian matrix is it is the matrix where the first entry is the partial derivative of the first entry in your output vector with respect to the first entry in your input vector. The second entry in the first row is going to be the partial derivative of, again, that first entry in your output vector divided by the second entry in your input vector. And however many entries you have in your input vector, so you have n entries, that's how many elements are going to be in the first row. Then, in the first column, the second entry is going to be the partial derivative of the second entry in your output vector with respect to the first entry in your input vector. And then the final entry in the first column is going to be the partial derivative with the nth entry in your output vector with respect to the first entry in your input vector. And then you can probably figure this out, but down here you'll have partial derivative of fn over partial xn. Now, in this video I don't want to confuse notation. I really don't want to confuse notation, and so let me point out that these subscripts are supposed to represent the entry number in the vector. Okay. And also the same thing for these subscripts. Those also represent the entry number in the vector. Whenever we were using the Newton's method formula, these subscripts represented the iterate number. And so we use subscripts here in this lesson for two completely different ideas. And I hope that's clear, and you can always ask me if you have any questions about that. But this Jacobian matrix is a really nice matrix. And again, we're not actually using the Jacobian itself in Newton's method, but we're going to use the inverse Jacobian. So if I say this is J, then Newton's method is going to have this vector xn plus 1 is equal to this vector xn minus, this is a vector, this is a vector, this is a vector. All of these vectors have n entries. This J inverse is a matrix. It's the inverse of the Jacobian matrix. Now, I said in a previous recording that not every square matrix is invertible, but every invertible matrix is square. And since I need to take the inverse of the Jacobian, that means the Jacobian must be square, okay? The Jacobian must be a square matrix. And so for this to be a square matrix and actually consider all of the output values and all of the input values, what this means for my multivariable function is if I want to use Newton's method, if we want to use Newton's method to find the zero of a vector-valued multivariable function, what this means for the function f is that the number of input variables has to be equal to the number of output variables. And if you had a different number of input and output variables, that would result in a Jacobian matrix that is not square and therefore not invertible, and therefore we can't use this multivariable Newton's method. So the number of input variables is also the same thing as the number of entries in my input variable x, and the number of output variables, of course, is equal to the number of entries in my output vector f. And that's how we end up with the square Jacobian. That's how we invert the Jacobian. That's how we use Newton's method for a multivariable vector-valued function. So this video has already gone on long enough, and so I'm going to put it to an end pretty quickly. The last thing I'm going to do is ask, do 3 points in 3D space fully and uniquely define a sphere? So here's my x, y, z axes. This is 3D space. And if you have 3 points just floating arbitrarily in space, and I tell you these 3 points belong to the surface of a sphere, does that fully and uniquely define the sphere? Or is there more than one sphere that could have these 3 points belonging to the same surface? Sorry, not the same surface. Is there more than one sphere that contains these 3 points on its surface? Or is there only one sphere? Does it make it unique? It's a question to think about before you watch the next video. We will fully answer this question in the next video.